Thank you very much. In my talk, I will focus on two things. One is TMS triggering EEG, and the second one is EEG triggering TMS. So when we use TMS and evoke potentials and measure them, we do this in order to probe the profile at the local site, but of course also hoping that we can capture the spread to other areas. So it's about local response, but also about cortical-cortical connectivity, and that method has been used widely now to look at pharmacology, paired pulse experiments, consciousness, and other things. A very seminal paper was the paper by Massimini showing these marked changes in the cortical response profile locally, but also globally, from wakefulness to non-REM sleep. During non-REM sleep, a very strong local response, but which stays local. When while during wakefulness, you have this spread and this complex pattern, which is characteristic of consciousness. I will not go into these data, but will kind of show you some a recent study which we did in a study on consciousness in order to figure out what are actually the contributions of the somatosensory and the auditory input when we record these TEPs. As you know, the TEPs the TMS gives a loud sound, which we try to cope with by putting a kind of noise into the ear at the frequency of the click, but the bone conduction can actually not be masked. So very few people would actually not hear something. I think it's quite impossible to completely mask it out. And of course, the somatosensory input through the trigeminal fibers is also cannot be masked. So we did a study using two sites in order to have a kind of within study conceptual replication where we put the figure of 8 coil in two different directions over the target, but then had a realistic sham condition where we put a bipolar electric stimulation and gave an electric stimulation while putting a TMS coil on top of it and creating the noise in order to mimic the input. We use SymNips to figure out whether the intensity we use is actually strong enough to actually evoke a local effect in the cortex, and the simulations kind of revealed that we were kind of focal, but also the realistic sham condition did activate the cortex, but very, very low. There was a little effect which kind of physiologically should not matter. We also did a lot of psychophysics, which are difficult to see here, but it was actually very difficult to do a realistic control. We were kind of able to match the intensity, but also the overall unpleasantness. But for the noise and also for the focality, it was actually not possible really to do this. So because the electric stimulation is conceived more sharply, so it's not a fully match of the input, but it was kind of possible to do it kind of roughly. When we then compared the evoked potentials, either by the TMS evoked with the orthogonal or the tangential orientation to the sulcus, to the gyrus, and then the realistic sham condition, the potentials are very, very similar. And this can be seen here in these topper plots, which show the different time bins. And you can see in the early phases it looks different, but also there it's quite similar. And the same is true when you look at the global mean field power, which is often used. When you then look at the electrodes which actually significantly correlate in time, these are the black electrodes for the different time bins, you can see that even at the early phase, there is a marked correlation. So this means that even when trying to match the input, it is actually quite difficult, and a lot of the contribution is actually not transcranial, but is actually somatosensory auditory. The same actually was replicated then for the parietal spot. Same thing, very similar shape forms. So the spatial temporal pattern very similar. And then also for the global mean field power. And here also a lot of electrodes kind of showing a correlation. For the late responses, basically all electrodes were highly correlated. For the early ones, some local effects were kind of different. When you then do a point-by-point correlation, so you use all electrodes and you look at each time bin and you look how they actually correlate in each subject at each time bin from condition to condition, and you compare the TMS conditions with the sham conditions, you can see the correlation rises immediately after the stimulation and reaches actually kind of 0.8 in terms of R. So it's a really strong correlation, and it actually kind of follows the time pattern. And this is true for the frontal and for the parietal. So there is a lot of similarity, which actually challenges the use of this method in terms of looking at connectivity, but also local response profile. So you can use it, but you need to have a realistic sham condition in order to figure out whether your effects are really transcranially induced or whether they are peripherally induced. What you can do is you can take this sham condition and there's a poster by Leo Tomasevich, which you can check out, where we actually then use the information from the real condition, from the sham condition, and do a subtraction approach, and then you get a kind of signal which most likely is induced by the TMS. This is the red curve. You can see the blue curve in this third line. You see this is the curve, but there is some data left, which is most likely used to related to the real TMS. So this method is in a way important. I'm not saying it's not useful, but it needs to be used with care. Now I'm going to the EEG-TMS part. So this is just flipping it. So now you're using the EEG information in order to trigger a TMS pulse, and that gives you a kind of possibility to actually target the power or the phase of a given oscillation. This is something which we do in a larger project in Copenhagen, which actually aims at kind of doing a state-informed closed-loop stimulation. The whole work was already kind of started back in Kiel, where Till Ole Bergman conducted a similar study where we looked at the slow wave sleep. I'm just showing this for historical reasons, but also for showing the proof of concept that this works. So here we target the up and down state of a slow wave and compared the different potentials. You can see the gray one is basically during wakefulness. You can see that the TEP during wakefulness is much smaller. It's much larger during sleep. And you can see that all the kind of different peaks that can be evoked in the TEP are stronger when you stimulate the so-called up state compared to the down state. For the early one, it's quite locally restricted to the site of stimulation. For the later ones, it's more global. When you then look at the in a wavelet analysis, what happens else, then you can actually see that it's not only the slow wave that is basically targeted, but you can also see that the spindles, which are coupled to the induced slow wave, which the TMS induces a kind of slow wave during the up and down state, then you can see that the spindles that are grouped are also stronger. So it's not only evoking a potential and making it, but it also kind of evokes the pattern, the natural pattern that the brain would induce. So it's also kind of affecting the spindles that are triggered in this kind of motif of the slow wave. This motivated us and others to go to the wakefulness, where you have also prominent rhythms like the alpha rhythm over the occipital and the motor pericentral cortex. And since I'm a motor control researcher, I was very much interested to target alpha and also beta during during wakefulness. There is actually very interesting literature which is worthwhile to know when starting this. I think I'm focusing here only on the alpha data published by Ole Jensen's group, which is kind of invasive data where you actually look at the different phase and power of alpha and then look how is the mean firing rate. And a very important finding was that basically when you have a high power of alpha, you have actually a low firing rate. And vice versa. But then you have also a phase-dependent modulation, which means that you have, when you enter at the trough, then you have a higher firing rate than at the peak. But recall, when you have a good phase, that means you have a high power. So that means that you actually have a low excitability. So overall your excitability or your firing rate is lower, but it's then modulated. So it's not a very straightforward kind of relationship. Power and phase have to be recognized. Early studies have done a kind of post-hoc sorting approach, both over the visual cortex, looking at the visual alpha. This is here shown on the here to look at phosphines, but here's for the motor cortex looking at the MEPs. And it was found that when you have a high power, then your MEP amplitude is on average smaller. If you have a low power, then it's larger. And for the visual cortex, it was shown that if you have a low alpha power, the probability to evoke phosphine, the phosphine threshold, is lower. So we have a kind of, which is actually fitting very nicely with the data by in the animals. I'm now focusing on two kind of results. One is a study recently published by Ulf Siemens group in Tübingen. They used exactly the same approach with slight modifications and used a kind of a fast recording fast sampling EEG system in order to focus on the alpha phase up and down. And what they found is that basically there's a marked difference in the phase modulation, showing that, as predicted by the literature, that in the trough you have a higher MEP size. This is shown here, and a lower when you're in the peak. And if you have a random stimulation, you are in the middle. These are two different experiments done by the same group, so it is a within-site replication of this. Important thing here to know is that the phase readout was a so-called yacht montage, where you have kind of a pseudo-monopolar montage, which basically is used here. And another important issue here was that the subjects were highly pre-selected. It was only subjects with a really high alpha. So 2/3 of the subjects were not included in the study. A thing which was also relevant for this paper, which actually has not been reported because of a kind of fixed effect analysis was negative, but there was a clear power effect in the data. So when you look, this is basically a single subject's data of all subjects that have been studied in the second part of that study, and you can see in red, and I marked it a little bit, you can see the positive slopes, which are slopes showing the MEP relationship to the power, and actually there's a consistent power effect for the trough. So this is the blue ones. So in each subject, the slope was positive. So even that was not reported in the study, there is also a power effect in that study. So you have a power effect and a phase effect here. And the power effect goes in the opposite direction, but as you would expect. So the more power you have, the higher the amplitude. Now I would like to report the results we obtained. We used a similar approach, a similar hardware approach, but rather than using this yacht montage, we used the online source readout using a source weight map, and then looking at the source and basically looking at the expression of the source, using then a Morlet approach to trigger. So there were slight differences in the way to set it up. But otherwise was quite similar. We used blocks of trials where we looked at 4 different phases: 0, 90, 180, and 270. And we always intermingled trials where we actually gave TMS with fake trials where we only set a marker in order to figure out whether we did it right or not, and looked at the motor evoked potential. Overall, we did 3 experiments, and they all gave different results, so I have to go through them one by one. The first one is actually where we used a flexible source projection, which accepted not only radial but also tangential dipoles, which actually are also picked up by the yacht montage, and we used a biphasic stimulation like the Tübingen group. Here we didn't find any effect on the MEP amplitude, so there was no effect of phase for any of those phases if you use just a simple random effects model. If you use a kind of model where you actually implement the power and have the power as exponential variable, there was actually kind of a factor of the phase modulated by the pre-stimulus alpha power. And you can see this here, the red, here you have a positive slope, which is actually the same as kind of, which has previously shown for power alone. So you have actually an effect of the amplitude with higher amplitudes only for the trough phase when you have a high power. And actually this was recently replicated or shown by a study at NIH by Leo Cohen's group, where they actually did a post-hoc trial sorting of 600 trials and then looked using a yacht montage kind of modeling approach, and they see the same thing. They see here only for the trough, but not for the peak. They see actually this kind of power phase interaction. So there's basically a kind of replication. So all the 3 studies basically show a power and a phase effect, and it goes in a way that which is kind of, from the PowerPoint, different as we would expect from the animal data. Then we did another study, which was, here we use also this flexible source projection, but now we use the monophasic stimulation. And in that study, we basically, at the random effects level, just looking at the MEPs alone and not looking at the power, we didn't find anything again. So basically, from that point of view, the conventional way of looking at it was negative, and we also didn't find effect of the interaction. If any, we found exactly the opposite effect. So we don't know what this means, but it seems obviously critically whether use a mono or biphasic pulse, and this has to be explored. And the last study was basically using now a radial source projection. So we only looked at the radial source, so we didn't allow for tangential sources. And again, we didn't find any effects when we used just a simple random effects analysis. But if we then consider the power, then we see actually a power effect, which is the one which you would expect from the monkey studies. So that's basically from the in vivo studies. Here it's basically a reduction in the power related. So the more power you have, the less your MEP amplitude. So the conclusion is TMS EEG, yes, interesting method, but a lot of peripheral confounds that have been kind of discussed away in previous papers and needs to be respected in terms of introducing a realistic sham condition. State-informed TMS, yes, it's very interesting, it works, it's technically feasible, but the underlying neurophysiology is complex, and when you target the phase, please mind the power. And with that, I would like to conclude. Thank you for your attention.
Thank you, Hartwig, for the excellent talk. Are there any questions? Well, then just maybe one question. Your talk was about the combination of EEG and TMS in this way. Would there be also place for another modality in these kind of studies? So is there a place for fMRI as well that could help in interpreting some of these results?
I think best thing would be to do all three together. I think Alexander Sack in Maastricht is doing this, has also shown some, but that's quite difficult to do. But I think it would be really interesting to at least do both modalities, fMRI and TMS and EEG TMS kind of in parallel. Yeah, I think that would definitely be very interesting, but also the spectroscopic things. But of course, the temporal resolution and the sensitivity is different. So it will be complementary, but not easy to be matched. So the nice thing would be actually to do all three in one time.
Any more questions?
Just one.
Yes, please.
Thanks, Hartwig. One question to the realistic sham condition. Of course, we all know TMS is difficult with sham condition. So what do you think about a good, let's say, control group, for example? Would it be an alternative?
No. Because if you see a group effect, you can simply not disentangle